Okay, let's start. So this is the let's say the layout of the presentation. I want to start with a very brief introduction. What are the main features, the main characteristics of masonry structures or masonry material that we want to capture with, we will try to capture with test. Something could be overlapped or maybe similar to what Corrado discussed, I think, two presentations ago when he spoke about numerical simulations. Actually, this presentation is complementary of these topics, because here the idea is to get parameters that we can use that can inform our numerical models. After this small presentation, I will introduce a test on masonry structures. Before speaking about non-destructive test, I would like to spend a few words about other tests which are much more accurate, give us a lot of information, but however they come with some sort of cost. In terms of damage produced on the structure. So for this reason, they are not very helpful for historical structures, but can be helpful to understand why we look at a non-destructive test. What is the advantage of non-destructive test? So here, this point 3 is the point 3 and point 4 are the two main the core of this presentation. With in the point 3, basically the non-destructive test will be focused on evaluating the characteristics of the material. In point 4, discussing about structural monitoring, we look at the techniques to investigate the response of the structure itself. So instead of the behavior of the material, we look at the entire structure and trying to get information directly from it. And again, the what we get from this test is helpful to inform our models, our numerical models, or to improve the accuracy of these models. Finally, in point 5, in very last couple of slides, we included some reflections on how these techniques can help, can enhance our project, our objective. So probably it will be a sort of assist for discussion after the presentation. I don't know why is it. Probably it's better here to switch the slides. Okay, so regarding the first brief introduction about masonry structure. So how is very intuitive to understand. So when we look at the masonry material, and in particular the mechanical characteristics of material, we need to bear in mind that the characteristics of this material are strongly characterized, are strongly affected by the nature and the shape, the regularity of two main components. One is represented by the stones. Most likely stones, if when we speak about historic structures, most likely bricks, clay bricks, when we have much modern, more modern buildings. And the other component is the mortar, so the material used to connect two stones together. So the strength, the maximum force that this material can sustain, and the ductility, and for ductility we mean the capacity of displacements or deformation the structure can have without failing. So these are two parameters, these are two characteristics very important for our assessment from the structural point of view, strongly depend of these two components, and also how they are assembled together. In this picture here, are represented two typology of masonries. The one at the top of the slide is we can say a better masonry in terms of mechanical point of view, because the shape of the stones is much more regular. We can see a sort of regularity in the bed joints, almost horizontal. Quite different if we compare what we have at the bottom part, where the shape of the stones is much more irregular, and also the organization of the stones is more irregular within the panel. In conclusion of this, however, if we know the characteristics only of stones and mortar, we can have an idea what could be the behavior of masonry, but we cannot estimate directly the characteristics of masonry when given the characteristics of bricks and mortar. This is fundamental. This is linked with what we are going to discuss today, and in particular the non-destructive test try to look at the masonry as a global material, not unit by unit, stones by stones, or mortar itself. Another quite challenging problem, but very common for historic structures, is that the walls are not, is very rare they are solid material. So even though we have a significant thickness of the walls, actually the real walls, the real good masonry generally is outside, is the two leaves externally on the close to the external face of the wall. Internally is very easy to get a very poor material, sometimes even soil inside the wall. So this is another aspect which make very difficult for us from the engineering point of view to characterize mechanically what we have and to assess the structural behavior. Again, non-destructive tests have been developed also to try to help in this for this challenge, let's say. So some tests are designed to look inside the wall without opening any holes to try to limit the damage on the external part of the wall. But this is from one side very common, from the other side makes put on the table a very big challenge for the description of masonry, of historic masonry, basically. So as a result of this brief introduction, we can conclude that we can have a lot of masonry typologies. When we speak about historic structures and we say the word masonry, actually it is not enough to characterize the material. We can have from a very good masonry arrangements material moving down until very poor mechanical material because of the shape of the stones. The arrangement is very regular. The mortar is degraded totally. So this is important to try to understand in which class of masonry we can classify the object we want to assess. In the literature, there are many attempts to classify, to define indexes, most of them empirically, to see if the masonry is good or is less good. I just reported probably one of the most used index is from this paper. It's called the Masonry Quality Index, Masonry Quality Index, and just to provide, let's say, a number to see where we are in terms of quality. As I said before, looking properly at the non-destructive test, let's have a look at what we have in terms of what we call partially destructive test. So in this case, the most common technique used for masonry structures is the flat jacks technique. Basically, these tools, flat jacks, are inserted within the masonry. This is because we need to cause damage. Then a fluid under pressure is used to deformate these jacks, and the portion of masonry included within these two tools is subjected based to two forces until it crashes. And so this test basically provides us all the information we need to put in. If you recall what Corrado said in terms of mechanical models, numerical models, so here from these graphs showing the variation of the variation of length between these 2 points, what is called the D here, and the force that I'm applying. These for us are, let's say, self-explaining the mechanical behavior of masonry. So in principle, we need whatever we want for our models. The cost is in terms of damage. So this test cannot be, is very rare. They are performed in historic construction because of this damage. Other destructive or partially destructive tests are endoscopies in which we consider small holes and look inside what we have internally. Again, these are very helpful to see if the core, the inner part of the wall, is with the different materials, but it produces some damage that we cannot restore. So we need to accept sort of damage. So basically, these are the real reason why non-destructive tests have been developed and are becoming very popular for historic structures, historic masonry structures. The other disadvantage of destructive tests are that they are expensive. So due to budget limitation, people can realize very few of them. If we look at the bottom part of this slide, I tried to summarize the advantage to cover these limits. Non-destructive tests are very easy to perform, less expensive, very cheap, and in one day you can perform hundreds of tests. However, they come with some drawbacks. One is that the interpretation is not very straightforward. There is a experience needed to correctly interpret the test, and also the level of uncertainty is very high. And again, generally, when we do non-destructive tests, we do a lot of tests to process them statistically. Right, now we are in the very, let's say, core of this presentation, in which I will try to introduce some of the main techniques that we classify as non-destructive and we generally use for masonry structures. The first one I introduce is the sonic test, and basically the idea is very simple. If we generate a sonic wave into the material, very similar to what we do when we throw a stone into a pod. In the pod, we can see the waves propagating. In the materials, is the same. The only difference is the magnitude of these waves are much smaller. But we can detect with specific tools, in this case a accelerometer, and we can estimate what we get from this test here on the right part of the slide is the velocity. So we measure the time, but then we can get the velocity since we know the space between the point where we generated the wave and the point where I'm measuring the wave. So in the end, we can have an information about how fast the wave propagates through the material, and this information through, let's say, a theory of waves propagating into elastic materials, something which is very well known in the literature, we can estimate the deformability of the masonry. So in the graph that we saw above, we can see basically this information, how easy or how difficult is it to deformate the masonry. Of course, here no any damage is produced because the generation of the sonic wave and the capture of this is totally, let's say, free of any consequence for the structure. I want to remark just one aspect. Somehow it's clear that we get a partial information. So among this graph that I said above is, let's say, what we need for our models. Here we get only part of this information, only the initial part. So somehow non-destructive tests produce a lower level of information in terms of what we need. However, since in the literature there are many empirical relationships between the elasticity characteristics of the masonry and for instance, the ultimate strength, we can get help from this literature. So even the information is partially, but this is very, very beneficial, very, very helpful to calibrate our model. Another test which is based on the same physical principle, we just change the post-processing, is what we call impact echo test. And so basically what we do, the operation is very similar. We have one tool to generate a wave, a sonic wave. In this case, generally is a hammer. A particular hammer which is equipped with the devices to register the force transmitted on the wall. So with this hammer we produce a sonic wave, and in this case we are interested in this reflection. So when we have any discontinuity, in our case, for instance, at the end of the wall, the external leaf, and the starting of the inner pore material, then this wave is reflected. We capture more or less at the same way with an accelerometer this signal. Processing this signal, we are able to estimate the distance, basically the thickness. So some tools, some software have been developed to give you a map of how thicker is the wall you are investigating, even if you do not remove physically any part. Similar to what when we go, let's say, to have a tack or something for people. Here the concept is similar, let's say, and the object of our measurement is the thickness of our wall. Similar to the echo test, we have the GPR test. It's very, very similar. The principle and the idea is similar. It changes just the nature of the wave. Above, we had the sonic wave produced by the hammer. Here is an electromagnetic wave produced by a specific tool. And here we can see at the top of the slide the execution of the test, which is quite simple. Generally, these tools have a heavy part that you can put on the ground, and one light part, which is the antenna, that you can move throughout horizontally and vertically your wall. And this is the output at the bottom. And these irregularities are basically the points where the wave is reflected. So this output is quite clear. So it's very easy to see that it was a very regular brick wall, and it's very easy to see the brickwork through the masonry. Sometimes when the material is much more irregular, this output is much more difficult to interpret. But again, it's very helpful to see the quality of the material we have into the within the wall, and how far is this material from the external part. So if you want, this is a geometrical information that in the end we get from GPR and echo test. Let's say another non-destructive test are the thermometric measurements. Basically, with specific thermal cameras, we can capture the temperature of the external part of a wall. This test, of course, can be useful in the context of climate change. However, the information they provide is, let's say, much more broadly than climate change. So any difference of temperature between one part or the other can be let's say, be used to try to detect damage or defects or whatever. So they are largely used in surveys, in situ surveys for masonry, and not only buildings. Similar to other tests, are very easy to perform. So very quick. In a very short time, you can survey the entire building. And we are coming, I think I am most on time. This is the last class of non-destructive test that I want to introduce. And is quite different compared to the others we saw above. All the tests we saw before were related to head as an aim to get information about the material or information about the wall, the internal thickness. Structural health monitoring or dynamic identification is a non-destructive test which tries to see what is the response of the structure against let's say service loading. So any structure we can see, even if is impossible to see by our eyes, is subject to continuous vibrations due to the fact that the people walk inside, vehicles pass around. So very small amount of vibration that if we are able to capture, then we can collect information about what the response of the structure is. And what we use basically are again accelerometers, and by means of these devices we can collect the acceleration shown by the structure at, for instance, different levels of different point of the building. In particular, this case study has been investigated by Giuseppe and his colleagues, and this is one of the most important buildings in the city of Catania. It's basically the city hall of Catania. And so this is just to give you an example on how generally historic buildings are complex in terms of geometry. And the problem is that we have a lot of assumptions to do in our model. And of course, we are not sure if we are very close or not in our modeling, if we are capturing the main feature of the structure. And so as you can see in this slide, in this case study, the plan is very complex. We have a lot of levels, so irregularities, whatever. So what have been done in this case study, but what it is also what is generally done. A number of accelerometers are disposed along with the plan of the building at different levels. And here on the left part of the slide, we can see the disposition of the accelerometers. And it's important to consider the extension of the building, because we generally the behavior of one part of the building compared to the other could be totally different, mainly in historic structures. And the result of this of our elaboration of these accelerations provided by the accelerometers are what we call the shape of vibration. So each building, there are complex mathematical demonstrations, but the idea is quite simple. Each building, each structure has some shapes that it prefers for vibrations. We can isolate these fundamental shapes by means of the accelerometer we get from the accelerometers, and these natural shapes that we observed experimentally can be compared with the prediction of the numerical model. We provide numerically a sort of approximation of these natural shapes of vibration. Well, if the model is predicts natural shapes very or close, let's not very close, but enough close to what we observed experimentally, we are confident that the model is well calibrated. Otherwise, we need to adjust. We need, for instance, to revise our hypothesis in terms of materials. For instance, performing more non-destructive tests at the level of the material. So this sort of iterative process is called in the literature model updating. It means we operate some changes in our model in order to make the numerical predictions and the observations in terms of natural shape of vibrations as closer as possible. And this is what has been done also in this case study. And here, what you got here in these graphs is the number of iterations. So the numbers of changes producing the model to try to capture the experimental shape of vibrations. And this is actually this paper would be presented in the conference in Lisboa in July 2025. Okay, so let's say I finished to present all the contents of this presentation. Hopefully it was clear enough to see what we have in terms of techniques if we want to investigate an historic structure. Here in the last two slides, we tried to reflect on how these techniques can be used in the range project. So let's say we will perform a number of non-destructive tests in a range project, mainly in the two case studies we have, and the two material case studies, and I refer to the church and in particular the dome of Ragusa Ibla and Durham Castle. In Ragusa Ibla we already performed the test, and let's say these are under post-processing. In Durham we will perform them in July this year. It will provide us information about the materials and the geometries of the walls, and we will use this information in two ways basically. One is to calibrate our models, as we discussed in the previous slide. And here is what is represented on the right part of this slide. As soon as we have a numerical model that we can judge as accurate, we can use these models to investigate numerically different aspects. For instance, we can impose to these models some variation of temperature, since we expect the increase of temperature by X degrees in the following 50 years, for instance. And then our models can predict what happened. So one first important contribution would be to get information to calibrate models. The other way in which we want to use a non-destruct test is to characterize the basic units of masonry, stones, mortar, to try to replicate small samples in our lab in order to perform a physical test in the lab. Of course, we cannot only use original units, because we cannot ask to remove pieces from the monuments, but we can perform a non-destruct test on the units in situ, and we can perform the same in artificial units, and we can compare if they are consistent or not. What all the results of this analysis, which we want to, let's say, to explore as much as possible until the end of the project, may be the object of specific guidelines that we can discuss with the stakeholders, and potentially also to include them or part of them as a suggestion for community plans or other documents like this. We can also include in training events. The idea is to make this test as let's say, visible, in the sense that it's not very common to have in the engineering practice, even for engineers, to have a knowledge about this test, how to use this in order to get reliable data. Is something that requires some, let's say, practice. And the experience that we are doing and will do until the end of the project can be finalized in a sort of, let's say, this sort of guidelines, policy documents. Maybe the name could be different, but something that can be shared with the communities, with the local practitioners. I concluded, I think, almost on time, 40 minutes. And thank you very much for attending the presentation. And please, if you have any questions or anything you want to discuss, I'm happy to. Also, Ashraf and Giuseppe may want to answer the question eventually.